has also received the prestigious INSPIRE, that is, Innovation in Science Pursuit for Inspired Research Fellowship for Academical Excellence by the Department of Science and Technology under the Government of India.
So, ladies and gentlemen, please put your hand together for our today's guest, Mr. Nikhil Srivastava. Welcome, sir.
Welcome, sir.
Thank you, Umesh and Anshu, for this overwhelming gesture for me. Bit of nostalgic for me, as you guys are, in a way, my junior from the college also. Most of you are, and it was really overwhelming. Shall I start my PPT now?
Yes, sir.
Not wasting my time. Okay. And sorry, you guys are not. You guys would have to wait for that purpose because of a few technical glitches.
No, sir, it's fine. That's not an issue.
Yeah. So, can you see the PPT right now?
Yes, sir, it is visible.
Okay. So today we would be discussing about the production logging. As a petroleum engineering background, you guys would have to have a kind of background knowledge of tools and technologies of the production logging tools, and more so, it is important for you guys to know the production related problems when the well has already been commenced. So for that matter, interpretation of this production logging is of more importance for you guys. And tools and technologies are basically important from the operational cost point of view, which logging interpretation team and other petrophysicists take care of. So I would be touching the technologies also, so that you can be aware of what is going on into the industry right now. So in the introduction slide, I have mentioned this tool stack, in which you can see, let me on the pointer, you can see this spinner in the bottommost part of stack, which is the
Excuse me, sir. Sir,
Yeah.
actually, the screen is totally white. It's not. Screen is not visible.
Screen is not visible.
Your presentation is not visible, sir. Yes.
Just a second. Is it visible right now?
No, sir. Sir, you close it and again present, I guess.
Okay. Can you see my screen right now?
No, sir. Sir, I guess it will be clear if you stop sharing and then share it again.
Okay. So I have stopped sharing right now. And
yes.
Shall I start sharing?
Yes, sir. Okay. Yes, sir.
Your entire screen. Okay. So I have already shared my screen. Can you? Okay. It is presenting my screen right now.
Yes.
Okay. So can you see right now?
Yes, sir. Clearly, sir.
Okay. Yeah. So I hope you guys can see this tool stack in the introduction slide. In this slide, this tool stack has a few of the tools which are actually important in the industry. These are conventional tools basically, and most of its use is right now prevalent in the ONGC specifically, and few of the advanced tools are also there, which Schlumberger and Halliburton sort of companies provide, and few of the assets like Mumbai assets of our ONGC, they use it. I can share that also technology of that those advanced tools also. Uh, but the log and interpretation part, I could not share with you guys in this presentation because of some restrictive policy of ONGC right now. They cannot share the logs and other specifically advanced logs of crucial areas like Bombay High and etc. So for that matter, I could not arrange that, but still we would look into the technology and its how it works, its working principle. So to start with the spinner, the lowest most technology in this tools in this stack, this spinner. This is also called flow meter. This is just the technology which we are using. Conventional tools and advanced tools, and there are some other tools that are actually just used as confirmatory tools to these conventional and advanced tools. Starting with this flow meter. So the flow meter is basically a tool which has a kind of impeller or spinner that we call it in usual manner. So this impeller basically revolves, and this revolution of this is due to two things. One thing is that we are running this tool stack with wire lines, so that wire line running and viscous drag force that is into the wellbore, that actually gives kind of force momentum to this spinner, and that is how it revolves. And due to that revolution we have a kind of measurement that basically gives us flow velocity, and this flow velocity eventually with some empirical formulas gives us flow rate. So that flow rate is basically important for us and to identify how and why it is actually being happening in the well that the flow rate has gone down and why flow rate has gone up. So to deduce such kind of problems, uh, we run this tool, and this gives us a fair idea, qualitative and quantitative both. So this measures the fluid velocity as it is mentioned here. Spinner rotation is converted to pulses. Those pulses are like calculated in the form of, converted into electrical and digital form, and through telemetry that is shown in this first slide, it is sent to the software that is in the truck, logging truck that we use to record. So those electrical signals actually gets converted, and uh, we convert again that those electrical signals into the revolution per minute. And there are types of flow meter that are such as continuous spinner and flow diverter or petal basket spinner. This you can see that this is inline spinner. There is a kind of spinner inside this hose sort of thing, and fluid enters into it when it is going down. Fluid enters into it from this side and exits from this side in the well bore, and and thus this spinner revolves into this hose and gives the measurement through this electronic device that is connected to this. And we'll be looking into the working principle also, but for now it is important to see that this tool has kind of OD of 1 to 3 by 8 inches, and that is how it is very important to run into the tubings where any kind of tubing leakages and other sort of problems like R3 packer leakages can be identified into the tubing through this flow meter. And secondly, this is a diverter basket type of flow meter. In this fluid enter, this is first thing first, that it is a motorized kind of flow meter. It can be used both in tubings and casing. This motor, when we open this motor, this cage kind of thing is this opens, and fluid enters into it, and this inverted funnel shaped thing, it diverts the fluid into this part, and here we have a kind of small spinner that actually measures the revolution per minute. And this flow meter is very important because it can be used in both tubing and casings. And for that matter, this funnel gets all the flowing fluid into the well bore into it, and it diverts in this spinner. So eventually we can think that we are getting all the fluid into this, and we measure the fluid velocity of whole fluid at a time. This thing cannot happen with this, because a certain amount of liquid, this inline spinner can have certain amount of liquid in this, but this has a larger cross-sectional area. That's why the fluid enters into it, can be assumed as it is entering right from it is entering into the wellbore from formation, and after that it is coming up and going into this just as I mean just as it is diverting all the fluid into the wellbore. And this one is the full bore continuous full bore this bore sorry this this is continuous full bore uh, flow meter. This is CFB. This is called CFB. The drawback with this full bore meter is that this cannot be this assembly cannot be run in the tubings, because this assembly is designed in such a manner that it collapses in the tubing, and as you run down into the well bore, it opens as it comes out of the tubing. It pops out and opens into this kind of structure, and thus this spinner or full bore meter revolves into the well bore, having the flow velocity of fluid into the well bore. Moving on to the next slide. Yeah, so to understand it much better, you guys might have seen this paper windmill craft, and we all would have, I guess, would have made this in our childhood. So considering this into the mind, all the flow meters have four blades like this only. And what we would do in the childhood, that we would make it and run against the wind, and so that it revolves faster than faster and faster. So we would run against the wind, and that's how we would play with it. And in a similar manner, if you think of this full bore meter, just sit on the just sit on that full bore tool, and as it you can think that you are running with that full bore meter into the well bore, and with that the sign of this revolution that this full bore meter, this spinner is doing, you can think of that in that manner. One thing I want to mention here is that these tools are basically tools are analogous to the medical medical field, just like radiologists do, or some diagnostic studies that are being done in the medical study. You can think of that, and these kind of wellbore full wellbore meters are just to diagnose that, and after that interpretation of that is very important. So in that manner, moving on to the next slide. Yeah, so what I was saying, that just sitting on that full bore tool, just imagine that we are running into the well bore. So as soon as fluid will face this spinner, the spinner will start rotating in the clockwise manner. So that in the industry wide practice is that is conventionally we conventionally put it in the positive quadrant, and that's why it is given the positive sign. And when the wind will blow from the back, the spinner or that particular the paper windmill, that will actually will start rotating in the anti-clockwise or counterclockwise manner. Similarly, if you will sit on that and supposedly in an injector well, the liquid is coming into the well bore, you will see that spinner is rotating in the counterclockwise manner. So that sign we uh, thought of as we put industry-wide practice that we would take it as in the negative quadrant. So that's why it is negative. And measurement, what we measure with this flow meter, that is pulse and revolution, that actually it how much it rotates in one see this spinner has a pitch, and just like nut bolts have pitch, this spinner has pitch. One rotation gives one rotation of 2 pi r gives a measurement of one pitch, which actually sends the signal to the electric wireline telemetry that one pitch has been done, now one revolution has been done. So that's why that's how it works. And second thing is that threshold velocity. This full well bore meter is having a spinner mechanism, which actually when we would be running into the well bore in the static condition, when there is no any kind of fluid is flowing into the well bore, there is static fluid into the well bore, then there will be some viscous drag force that will be impounding on this full bore spinner. So on that spinner, when this viscous drag force would be coming, there would be some kind of minimum threshold that would be required for this to rotate. So that's how we have to calculate that threshold velocity, so that the average velocity of flow volume can be calculated. We'll be coming in the next slide for that. And pitch of the spinner, that I told you that in the stationary pass, when one rotation in the well bore, one rotation of spinner would be completing, then the signal will be sent to the telemetry that one rotation has been done. That's how the 2 pi r of the revolution gives us the calculation sort of thing. And it is this full bore meter, full bore spinner is run in both logging up and logging down in different speeds. Speed matters because suppose there is fluid volume that is coming into the well bore and there is not much of pressure. So in that case, what would happen, that there is not much of force that is coming to the tool. So in that case, what would happen, that we would see that spinner is not working properly. Somewhere it is working in a different manner, like it is rotating slowly, but again it stops. Such kind of things happen. So there must be minimum fluid volume which is coming in the production well for this to work. And in injection we have a kind of control, so that in injection wells this kind of requirement is not necessary. So the calibration part, what we do, this blue line, you can see this blue line is for the full bore meter. When it is going into the well bore like this, and fluid volume is static, like no production is happening in the well, and it is wholly filled with the fluid volume. And suppose there is no friction and no viscous drag force is happening. So what would you see when tool would be going down? Tool velocity down means tool is going down. We are actually lowering down the tool into the well bore. So when we will be lowering down the well bore, a spinner will start rotating because there is no viscous drag force or something like that. So revolution will be fine and it will be proportional. Similarly, in the upward side, like we told you that I told you that this will be in the positive quadrant when we'll be going down. So this this convention has been made in this calibration also. And when tool will be pulling up the tool, similarly the revolution will be in the negative side, but we'll be seeing that it is proportional. It is increasing in the negative direction, like counterclockwise revolution is increasing. So this is how calibration is done. Now what happens that if you have some viscous drag force, so this will not start from zero. This will start from some point here. So in that case, what let me change the pen. So it will start from here. Why here? Because there would be some kind of threshold velocity that we discussed that is needed to run this spinner, and that's why this threshold velocity would be needed. After that, it will again follow proportional path that is parallel to this, and uh, in the same manner in the upward tool recording also it will be following the same path, and this is threshold velocity. uh, I guess I am clear till now, and moving on to the next part. Yeah, so I already drawn it here. You can see that after threshold it has started moving into the right when the tool is get lowering tool is being lowered down, and while we are pulling it up, we can see that it has shifted in the negative direction, and that too gives us a threshold velocity. And in the next slide, I have shown that it actually varies with the fluid form. I mean, what kind of fluid is in the formation. So for water, the for same speed, tool speed, water, this revolution will be higher. For gas, this revolution will be lower. Why? Because the viscous drag force that water will put on the spinner will be much higher. That's why this threshold velocity is low here. Here you can see the threshold velocity is some 10ish, and here it is some 5ish thing. So for that matter, gas is like considered of lower viscosity. So that's why it is giving the much higher threshold, and you can see the slope is little bit steeper in water case, and it is not that. I mean, gas flow rate is. Uh, you will have to have a spinner rotation, lower spinner rotation for more gas flow rate. So this slide depicts that. For water and oil, it is not that much differentiable. So that's why I shown this slide in water and gas, because here it is clearly visible and clear. Uh, these are the full flow meters that we discussed in the first slide. This is inline, and there are some technicalities. I thought some geoscience background people would be here, so that would be important for them to know the limits for how can they be run, because reservoir engineers or production engineers, they in the industry they give us kind of a requisition that you have to find out the problem. So what would do, we would first we would identify what kind of tool can be run, what kind of production is being coming from the well. So whether the tool is compatible with that production or not. So such kind of things have to be decided by a petrophysicist or a logging field engineer. So in that case, it becomes important to know the tidbits of what your tool is, basically what its limits are. So more threshold velocity, it works only for threshold velocity of 10 feet per minute. And for it works best for single phase flow, like if in the wellbore it is if you are doing injection in the wellbore, so it will be a very ideal tool to identify whether the injection some leakage in the tubing is there or not, or some injection profile is proper or not. So in that case, this tool can be run. And in the production well also, if velocity is greater than 10 fpm, so in that case also this can be run. But mostly we run it in the industry. From the industry point of view, it is being run in the well in which tubing related issues are there, so that in those cases it gives us the better idea what is being happening in the tubings. So it is good for well mixed multi-phase flow also in the deviated well, and but that again that flow velocity or threshold velocity must be kind of I mean greater than this range 10 fpm. This full bore, we talk a lot about this full bore meter because we are much interested in the zones which are perforated, because most of the problems occur in those areas only. Tubing mostly have a kind of leakage problem or something like tubing strings are not properly latched. So these kind of problems are, I mean, very few, and this can be identified. But this full bore meter is very important, and it gives us the idea that how what kind of thief zones are there, or is there any channeling behind casing or something like that. These kind of problems can be identified with this well bore type spinner. And the spinner size in this full well bore is larger, so it actually faces a large volume of fluid in the well bore, and thus gives us the realistic idea of what fluid velocity or fluid volume will be into the well bore. And it is self centralized, though still we put a second centralizer also, as I have shown in the first slide. So this this kind of full well bore spinners can work in less than 5 fpm also, and yeah, also it works in better low flow volume, low flow environment. And but the one problem that it faces in the multi-phase is that in case of multi-phase, uh, the threshold of this spinner is a little larger. So in case of multi-phase, if it is gaseous, the multi-phase has uh, multi-phase consists of gas. So in that case, this full well bore spinner gives some kind of an erroneous data. So we do not rely in case of deviated wells if it is multi-phase. And we rely on other tools. We'll see that there are other important tools. This flow diverter, as I told you that this is motorized centralizer. This is good for low flow rate, and as I told you that all the fluid volume once it extends, and this particular central part, it works as the centralizer. So once it extends in the casing, you will see that all the fluid is going into this and it is being diverted. So it kind of takes all the fluid volume, but uh, um, I would like to know from you guys that do you think that it will give the true full bore flow rate? Because in that case, even if the fluid volume is coming into this particular spinner here, but you see that the volume is significantly changed. So in that case, velocity will be literally very high here rather than here. So in that case also, we do have some corrections and some industry related empirical equations that we apply. You might be aware of this. Uh, in physics, we would have read A1 V1 is equal to A2 V2, something like that. In in the same manner, this is applied here also, and this velocity of fluid volume is calculated for actual, for fluid that is being in the wellbore. It is best suited for inclined multi-phase flow. Yeah. So the thing is that other full wellbore or inline type of spinners, they do not work very well in the deviated wells and in multi-phase environment. So in that case, this comes as a rescue for us, but the thing is that again, it brings certain kind of limitations that the flow volume must be greater than 3,000 barrels per day. So there are wells that can produce this much of liquid, but many wells do not produce in the deviated category. So in that case, it actually gives a little of limitations in our Mehsana asset. I do not want to comment on the other assets because the fluid dynamics in every basin and every kind of formation is totally different. Minimum 35 barrel per day. Uh, this is the limit in the single phase flow. If in the single phase flow, the minimum 35 barrel per day is flowing in the vertical well, then this tool will work and will give you the results. These are used to record stationary readings at depth of interest. So the thing is that it can also record stationary readings against the perforations, where you can just lower down the tool and put it uh, against the perforation intervals, and it will have all the liquid coming to it, and will give the stationary readings of that particular depth interval. Those stationary reading will be important when you will be interested in getting the fluid hold up. From there are several perforations being done in a well, and you want to know whether from which perforation actually the water is coming or water is seeping in. So what kind of tool can be run in that case? So in that case, you can run this as taking the stationary reading. In stationary readings, further with in addition to other tools, you can calculate the holdups, and that will give you the fair idea whether the water is coming from a particular perforation zone or not. So next, in situ calibration is not possible. So yeah, the calibration, since it is motorized, so you would not know whether it is actually being opened in the wellbore or not, just by pushing a button in the logging truck. So the calibration is done on surface. We actually try to calibrate it on the surface only because of that purpose, so that it can work, it can function properly into the wellbore. And uh, as I told you that there are several perforation zones, and you want to know the hold up, so it is reliable in the multi-zone wells, and it is more susceptible to damage because it is motorized. As I told you that once in the wellbore, it will be in the wellbore. You'll totally have to rely on the motor mechanics of this tool. So in that case, it might fail some of the time because uh, well behavior is sometimes very unpredictable. So the flow patterns, yeah. So in this also, uh, let me show you these two kind of flow, laminar flow and turbulent flow profile. So, in case of, uh, generally, what happens that our fluid in the wellbore, if it has pressure, then you will find kind of turbulent flow profile, and for that, laminar flow profile you'll find, but it is very rare in a manner that your flow velocity or the pressure in the well is very low, then only you can think of having a laminar flow, near to laminar flow, but it is very rare rare phenomenon. Mostly we find the turbulent flow, so we do have to correct. What we are actually calculating is the fluid velocity, and eventually the fluid rate from that fluid velocity. So to calculate that fluid velocity, we would have to have a kind of correction. So I mean, your this spinner is calculating a velocity of this particular area only. It is actually not covering this area or this area. Here also it is not covering this area or this area. So considering this as a kind of limitation, we would have to calculate the average velocity. We would want to know the average velocity of this fluid that is flowing into the well bore, and for that we would have to have some correction. So that's why in that case, the Reynolds number comes to a rescue. You might have read it in your 12th. So this Reynolds number, if it is, below 2000, so it is laminar flow, which is very rare, as I told you. And this flow transition happens when Reynolds number is between 2000 to 4000, and when it is um, more than 4000, then it actually follows the totally turbulent flow. And this is the correction factor profile for that, where that we would have to calculate. So if you are convinced that your Reynolds number is this, so correction factor, what we actually practice in Mehsana is that we apply the correction factor of 0.83, that I will show you guys in the upcoming slides. So here you can see that you can calculate the Reynolds number for the fluid volume by knowing the density, fluid density. For that, we do have a tool, and average velocity that is being calculated here, and then it is id of the pipe that is known, and then viscosity of fluid is also known. So you can calculate the Reynolds number, and you can apply that correction factor by knowing the Reynolds number of the fluid that is flowing to the well. Mostly in the Mehsana, that I told you, that it is 0.83, and it is near about zero point 0.8 for zero point 0.6 to, it revolves around 0.6 to 0.9 to most of the field of Mehsana and Ahmedabad. That's it. So this is the flow meter environment. Fluid comes in the different manner in different as they have different density and viscosity. These are intrinsic property, you cannot change. So there is kind of mechanism that they follow to come up to the surface. So in case if this kind of flow is there, there is a kind of bubbles of gas and oil you can see in the water. So it is the this kind of flow is called bubble flow. And slug flow, when you see that viscosity of oil a little bit higher, so in that case what it will come out on the surface in the form of slugs. So it will be coming out in the lumps, and again water will come, then again lump will come, then again water. It's sorts of come like this only. And again when it comes in a little crude, or this manner. So this is churn flow. This we do not see in Mehsana. Slug flow is very common, and bubble flow is also very common. And annular flow is basically the thing is that when you have some kind of water hold up, very low water hold ups, then only in this case water will be sipping from the sides, and whole volume of oil or gas will be coming from the middle. We see such kind of cases also in Mehsana. So problems in the Deviator wells while running this kind of flow meter. You can see here that perforation is here on the upper side is actually giving the production in the well. But what happens then if you have sump below this particular perforation? You will be having a kind of convection in the fluid flow volume. So this will be coming from here with force, and this will again after after coming to the tubing packers here, it will again come down to the tool, and as it is kind of uh, uh, natural that due to gravity, tool will be running on the lower side. So in that case, you will be seeing that tool is giving the erroneous data. Like you will be seeing that revolution is in the negative direction, and that too will come on your log profile. Uh, Let me tell you that you'll be thinking that when centralizers are being put here, so why, what kind of, what is the reason that this will be like this? But this convection happens in the whole well, because on the upper side, the due to gravity, this gas and oil goes in this upper side, and that's why it comes below after I mean uh, uh, I mean touching this packer, and that's why this convection gives this kind of thing, and it gives the kind of understanding for to the interpreters that some kind of injection is going into the well, but that is not the case. For that, this kind of, to eliminate such kind of qualitative interpretation, you must know the characteristic of your well, how it is giving the production and how much production is there. So with that, you can eliminate such kind of things. But industrial tools are also being developed, and they take care of such kind of things, and they correct it right there into the well bore, and we do see just the positive response only in those tools. So you have to give the prior information of production that yes, the well is in the producing profile. So circulating some water, yeah. Next is in the deviating wells, you will see that if as I told you that oil and gas being lighter will be flowing on the upper side due to gravity. So sensors sensors like in this or other sensors in the hold up hydro tools and density tools, they will give the erroneous data, because they will not read the gas and oil and the average. If you will average out, they will give most of the order, but this is not the case. So in this kind of deviated wells, we do run some specific tools, as I told you that though that basket inverted basket flow meter uh, is suitable tool to be run into such kind of situations. And mm, yeah, in this case also, you will not see that it is producing, but that is not the case. Again, such advanced tool like if you would know the flow scan or something like, those tools will know the real scenario in this. That's why in such cases we asked Schlumberger and Halliburton to run the special tools to identify whether there is a problem with actual problem with well, or there is no problem at all. It is just that the interpretation of conventional tools are being somewhere compromised with the limitations. So limitations, you see that we already discussed that threshold velocity limits the sensitivity of the flow. You have to have the threshold velocity that that can run that flow meter, and velocity correction must be done with the Reynolds number calculation. Noisy response due to type of flow. like in the in single phase, noise will not be very much, but two phase or multi phase flow noises come in the manner that they actually confuse our tool. So for that we do have kind of remedies, but conventional tools do get confused with the multi-phase more often than not. So response in the deviated wells, we discussed already that due to fluids like segregation, due to gravity, these in the deviated wells, these conventional tools do have limitations, and they do calculate some erroneous results. So we must have to be careful, and we as a logger, we do recommend the requisition team from subsurface or other people in the authorities, so that we can run other advanced tool from the third parties like Schlumberger and Halliburton that that have sort of array tools and flow scanner tools that can give the whole picture of the well. uh, Flow regime disturbance. Flow regime disturbance during up passes uh, are being seen, because the thing is that you see in the up passes, what we would see that production is coming, and you are also pulling out the tool. So with the production velocity fluid, the tool is also running in the same direction. So if low flow regime will be encountered, in that case, the spinner fluctuation will not be that much. So will not be able to identify that fluid is static, or it actually fluid is actually coming from the wellbore. So in the up passes, we have to be a little, I mean, uh, uh, careful that we know the production is production is good. It is more than 35 barrels per day or something. Coming on to the next tool, that is temperature tool. Temperature tool is basically nothing but a resistive thermal device, or kind of non-conductive surface on which a metal, mostly tungsten or platinum wire, is bonded, and it basically measures the change in frequency with this tool, and that change in frequency per degree Fahrenheit is again recalculated to get the temperature. And this is very awesome tool to know many of the things which actually full well bore meter or our diverter tool cannot give, like channeling behind casing sort of things. This is very basic and ideal tool to run to know such kind of problems in the well. So it measures the absolute temperature. Temperature accuracy is very good. It is, up to the plus minus 0.2 degrees centigrade. Resolution is 0.1 degree centigrade. And the thing is that in the temperature logging, we what we take care that we always log it while running the tool down. We never run it while pulling the tool in the up passes, because what happens that in the up passes, as you have already gone down and you have tool, because there is no telemetry that can tell the temperature tool that you have to record now and you do not have to record now. It is just a simple device, and which calculates the which is resistance based, and it calculates the difference and gives in the form of frequency, and thus that is again recalculated in the form of temperature. So what happens that once your tool is down, it has already measured all the formation temperature. So your tool is conditioned with the temperature in the bottommost point, and when you will be again uh, take the up pass, this will not give you the geothermal gradient idea. So in that case, you may get results, but you cannot rely on that, because every temperature curve that we log into the well, that is being tied with geothermal gradient. That is the temperature of subsurface that varies with per meter or per 100 meter. It varies 3 degrees per 100 meters. So near about. So we have to tie it up with that, whether it is how much deviation is with the geothermal gradient at that particular formation. So if you are taking the up pass, in that case, it is not going to give that idea. So it is always the curves are always recorded in the temperature tool in the down log only. And in short, the logged interval has some. So in the industry, when a temperature tool is asked to run from the reservoir engineers or production engineers, what we first thing we ask is for a sump, because the thing is that in sump only the fluid will be in the static format and it will give the actual temperature of that particular formation in and around. So that will be a tie-up depth where geothermal and temperature tool should read equal. So in that case, if sump is not of, tool stack is of 10 meters long, and temperature tool is at 5 meters, so at least we require 5 to 10 meters of sump in every well where we are running this temperature tool in combination with other tool stack in production logs. Multiple shut-in passes is required, because sometimes what happens that in flowing condition, your well is your well will give the idea that is not very much of idealistic case, because in that case what will happen that from some for perforation depth, your liquid is coming up to the surface and it is actually disturbing the whole ecosystem where the temperature was with geothermal equilibrium, and in that case what happens that you you would get something that is not I mean that much interpretable. So in that case, multiple shut-in passes at different intervals so that the temperature gets its equilibrium into the wellbore have to have to be there, and that's why we do have some 2 to 3 multiple shut-in passes at least in the production wells in Mehsana. And next is in the hydrofracking, we actually want to know whether the fluid that we have, for injected into the well for fracking, that has gone properly into the well bore or not, and how much horizontal or vertical extent of it that has actually made the fracture into the well bore can be we can have idea of that with the temperature log. We'll see that in the coming slides. So in that case, we run this temperature tool. Also, the flowing borehole pressure and bubble point pressure, water or gas injection, etc., helps in understanding anomalies against the perforation. That means that these kind of data, if we have, then in that case, what kind of anomaly the temperature tool is showing, we can have that idea in the particular well. So we do want to know that such kind of parameters from the reservoir engineers, so that we actually come to an accurate or near accurate interpretation. Injection and circulation before logging to identify pipe leakage. So if you guys suppose workcore engineers and other production engineers have circulated some liquid or some injection is being done before running this temperature log, we would have to identify to identify the leakages, if you are running that, and in that case, you are asking us to run the temperature log, so we actually avoid that in case, because that will not give us correct idea, because right after you have injected the or circulated the liquid, it will disturb the equilibrium of temperature, and that will not give the proper anomaly. In that case, uh, if you give us some time, like 4 to 5 hours, you can wait with your work colleagues and all. So in that case, we can identify the pipe leakages and any kind of problem that is happening due to the poor latch of this tubing or something. So we can identify that with temperature tool. So this is the condition of a well where the perforated zone is producing, and this green line is our geothermal gradient. Okay, so it proportionately increase, as I told you that for every 100 meter it increases more or less 3 degrees, 3 to 5 degrees. So in that case, this uh, uh, temperature tool, when it was run, it is showing that it is increasing here, and again it goes uh, uh, goes uh, it proportionately goes down, and yeah, on the surface it is showing here. So what can be inferred with this, that perforated zone is producing something that is hotter, and hotter fluid, and this hot fluid is coming up to the surface, disturbing the equilibrium in and around, and that's why we are our tool is reading the higher than the geothermal gradient, and that's why uh, this increase in temperature is there, and that is how we can infer that some kind of production that is hot, whether it is water or oil. In gas wells, we will see the condition changes. So whether it is water or oil, it is showing the increased temperature profile. Uh, in this, though we have read the full bore spinner, but we have not seen the logs. But an ideal log I am showing you here. This pink line, uh, below this is the perforation zone. This M dash. Okay, this this M dash is this perforation, and below this well bore is not showing any kind of fluctuation. That means it is seeing it as a static liquid. Okay, so there might be some viscous drag due to liquid, but the thing is that a spinner is continuously showing a constant value, and against the perforation it starts increasing, and revolution per minute increases, and here you see that till the up up to the well head, it is showing the same RPS. So full well bore tool is giving a kind of interpretation that yeah, the liquid is coming from the perforation, it is all okay. But the thing is that when you assess this temperature profile, you see that the curve has started increasing right from the value where m is been given, right from the depth where m is there. So from this you can infer that you may get confused that okay, so production is coming from here, so our temperature should increase from here to here. So in that case, it is not happening like this. It is increasing below m dash from m only. So there must be some kind of channeling behind casing, uh, uh, there might be the problem that uh, cementation would be poor, and fluid from this formation M is actually contributing behind the casing to the M dash, and it is coming with this into the wellbore. So uh, that we can interpret from this temperature tool, which is relatively very basic and less costlier than this full wellbore. So this gives us the information. After that, the remedial action can be taken, that is squeeze perforation and other kind of remedial actions can be taken. So in case of gas entry, in gas zones, the scenario changes because gas show kind of adiabatic characteristics in the well. When it expands, it cools down. It shows the cooling effect. So this geothermal gradient, uh, this static temperature log, this is a static temperature log, and this is sorry. Yeah, this is static temperature log, and this is showing us the geothermal gradient only. Below this gas zone, the temperature profile here is touching the temperature gradient, but suddenly after coming against the gas zone, it kind of decreases and again increases. Okay, so in the gas zone, it actually uh, gives us the cooling because uh, gas relatively expands here, and it gives the cooling effect. But again, when in flowing condition, this gas coming to the surface, this actually gets gets kind of into the equilibrium with the surroundings, and thus this difference is shown because there are other fluids that are in the wellbore also. So in that case, it will show like a difference here, but cooling will be against this perforation zone, and that will this reason is enough to know that yeah, the gas is being coming from this particular formation. Again, a gas zone along with this other perforation. Gas expands in the well as it enters in the well bore, and the expansion is adiabatic. As I told you, that this creates a cooling. See, this is again the temperature gradient, thermal gradient, and you see there are two profiles. So in this case, it is getting cooled. Okay, so from this perforation, you might expect gas. That's why it is the cooling is being done. There is no other condition that can happen in this case. If the cooling in the temperature log is shown, you can blindly say that yeah, this perforation zone might be contributing gas. That's why it is showing a kind of cooling effect. And this particular the profile that is shown here, that is when there is no gas. So if the fluid is coming, whether it is water or oil, and cooling is not being done, and it is following the regular increased path, so you can identify that yeah, it is not uh, I mean, it is water or oil, not the gas. And this, I guess we have already discussed it. Yeah, but this is another interesting case. Here you see that temperature is showing channeling, gas channeling. How it happens? Like we saw there that some channeling is behind the casing, but in this case this channeling is because of fluid, it is water or oil. So the problem would be like in this case would be like whether the zone would be suddenly producing with increased water cut, or like it will be suddenly producing more fluid in the form of oil. So yeah, that is always welcome, but the thing is that suddenly if it has gone from 3 meter cube per day to 30 meter cube per day, there might be some reason. So for that we can we can run this kind of production log and know the reason. And in case of gas channeling, you cannot identify it from the flow meter. It will again show just like that only. Static Due to static fluid run, there will be some RPS, and again it will increase against the perforation zone, but temperature will beautifully show you the cooling against this, where from where channeling behind casing is being done. Again this will increase and uh, try to attain the formation temperature, formation geothermal gradient. But as you see that this gas has started coming from this behind the channel, and again, yeah, here you will see that adiabatic expansion is adiabatic expansion has started, and you will see again a cooling profile, and then it will go on increasing into the wellbore. So these two anomalies will tell you that yes, channeling is being done into the well behind casing. So there are other cases where you can run this temperature tool and identify like casing leakages. Casing can leak due to several reasons, like there are corrosive gas that are coming, or there might be that casings are very old, and due to rusting it has got corroded, and there might be some contribution from that particular leaking zone. So in that case, if you run temperature, this blue line is showing you the geothermal gradient, and this green line, if you are having a kind of ideal condition, no leak, so you will be having just the perforation liquid coming into the wellbore, and you will see that gradually it has increased in the wellbore, temperature has increased. But this red line in the leakage cases, this kind of profile, red line kind of profile will be observed. Here what is happening that in wellbore, from where liquid is being contributed in this wellbore, here the temperature is lower than this, so average temperature here will be lower than what is coming into the wellbore. So again, if leakage is there, you will see that there is slight cooling of this anomaly. Cooling anomaly will be seen. That means it does not mean that there is gas or something like that. It just shows that the liquid is coming from this. Yeah, you can infer that if gas will come from here, you can say that the cooling will be much larger than this. But if a gradual decrease is being happen, you may infer that it is due to the leakage in the casing. This lowering of temperature is happening here. So it is capacitance or hydro tool. It is called hydro because it actually helps us calculating the water holdup. Nowadays, it has gone obsolete from the industry, but in ONGC we do run it to identify the water holdup in the excessive. In the wells which are excessively important, and the thing is that we cannot lose them. So for that matter, we do run this. This tool has a limitation that this will not give you hold up of water beyond 40% water cut, because in that case it will totally read the capacitance, dielectric constant of water, and this will be kind of this will be kind of giving kind of erroneous result that water is coming, 100% water is coming, there is no oil. sort of. So there is a limit with this tool that you have to have less than 40% water cut. In that case, a mix of liquid oil or gas with water will come, and this will identify the average dielectric values like this. Here you can see that for water, it is very much significant. Dielectric constant is very much significant, and this is not very identifiable with gas and oil. Between gas and oil, so gas and oil cannot be segregated, but water can be segregated with the hydrocarbon. So this actually can give us water holder, but again, it is best suited for less than 40% water cut. And uh, this tool is basically this tool works on the principle, as I told you, that there is capacitance that due to the intrinsic dielectric constant, intrinsic parameter of dielectric constant of every fluid, this changes, capacitance changes, and the output we get is in the form of frequency, and that is being again converted to the Holder empirical equation on the surface when we get the law. So sensor is basically a kind of isolated metal cylinder in which inside Vespel sleeve you can see, and there is a capacitor into this, and between this, when the liquid passes, it measures the dielectric constant. That's it. So tool principle is basically needed for the geoscience background people. You just have to, as a petroleum engineers, you guys, I guess, have to know from the industrial point of view that whether this tool will give you the water hold up, and that too for less than 40% water cut, which is nowadays very less. I mean, the such cases are very less in the brown fields like Mehsana and Ahmedabad. Here, water cut has gone beyond 60% or something. So this tool has eventually got obsolete. But yeah, we do use it in the crucial wells, as I told you. Uh, yeah. So this is the fluid density tool. So we have a density tool also, which is based on the radiation and the pressure difference. So
Please click on the hide button.
pardon?
Sir, hide button. Sir, actually, yes.
Okay. Now you can see it?
Yes, yes.
Okay. So fluid density in this, please mute the mic. Yeah, thank you. This fluid density, what it does, that it measures the average or bulk density of fluid volume. It works on two principles, like I told you, that differential pressure and the average density of fluid volume. So fluid density tool in what we use in Mehsana is of radiation type, and we use the cesium 137 for that purpose. This is the empirical equation that we that actually tool follows. We just have to run it, and it gives the bulk density. And this is based on the Compton scattering effect, where the gamma that is being released from this cesium 137 source is actually bombarded on the fluid, and it due to Compton scattering, it it uh, it gives the inelastic scattering, and the gamma that released from that scattering is recorded in the gamma detector. So that gives a kind of that gives the intrinsic property of this fluids in a way that there is kind of spectrum, energy spectrum for those fluids, and that is very unique for water or hydrocarbon. for oil and gas. So with that, it measures this particular formula in the tool physics only, and density of fluids is thus measured. This is mass absorption coefficient and source detector spacing. This is spacing, and NX is gamma ray counts received by detector. Count is being received here, and total counts, yeah, what actually source is actually bombarding on the into the wellbore. So that total counts is based on the radioactivity of this source. uh, yeah, so this is the gradiometer. In this, what we do that there would be silicon oil of known density in this particular setup in between the 2 points PA and PB. So it is like P2 is equal to PB. It is connected here. P2 is equal to PB, which is eventually PA plus rho GH. As you know that it is basic physics that at any lower point, the pressure would be rho GH times adding rho GH times that pressure of earlier point. So P2 P2 is being P2 has been calculated, and P1 is basically the difference between this TA and the difference of this rho GH. So this silicon oil is of known density, and that's why it is rho SOGH. And when you will have the difference, you will get this formula, and from there you will want to know this particular rho. That is the bulk density. Fluid is coming from here, going fluid from the wellbore is coming from here and going from here, and that's how I mean this rho is being calculated. This ratio RSO is uh, just rearranging these equations, and uh, silicon oil density is being calculated also with this formula. With wellbore pressure. This is empirical formula, so that is not of much. Uh, we do not bother about the this because this empirical equation is already being fed into the the tool, and that automatically calculates the density of silicon oil. So we do have to bother about this rho, and this calculate the bulk density in this differential pressure manner. With this, if the oil of density of oil is known, that is coming onto the surface, and the density from the gradiometer that we have calculated, we know that we can calculate the water hold up with this also. In this case, we will be having this kind of graph in which density of oil and water point where 100% water holdup is there is being drawn, and once we calculate this rho gradiometer from gradiometer, this will give since this is the mixture of oil or water or gas or water, so this will give the idea that how much water holdup is there. So this is one way of calculating water holdup, but gradiometer is not being used in the western region of ONGC, so cannot comment much on that. Gradiometer is suited for vertical well, and that is of low deviation, and it does not have much of accuracy. That's why we have purchased the radiation tool, which is equivalent to the density tool, if you might be knowing, to in the open hole that is being run in the open hole. So that is equivalent to that, and though gradiometer is more rugged, and it can be run in kind of any condition, and one thing that is very important, that this does not have any kind of radioactive material, and that's why uh, organizations like BARC and other regulatory authorities, they do not have we do not have to worry to take their permission in the kind of radiation tool. We every quarter we have to take the permission whether we can run this kind of tools and or not. There are some regulatory bodies that, like BARC, they actually keep records of that. So for that matter, it is just that a radiation hazard, to control the radiation hazard, these radiation tools are important. I mean, to we have to give the information of such tools to the authorities to run to the wellbore. And pressure tools are strain pressure tool and pulse pressure tool, two types of pressure tool that they measure pressure in the wellbore. There are other methods that reservoir field services do use, but more or less nowadays in industry, quartz pressure tool that works on the principle of piezoelectric effect is being used. Strain pressure were used earlier, but nowadays it has not been much in use. And principle is basically that the pressure induced strain in the sensor causes change in the electrical resistance. So that electrical resistance is being uh, recorded and being sent to the telemetry, and through telemetry in the wireline to the surface. And in the software, we the resistance is being converted to again in the pressure. So accuracy is good, and strain gauges are less accurate, as I told you that that's why they are not being used much in the industry now. And uh, response time, its response time is better because in the well, if you are having kind of low flow volume, in that case response you'll be needing the response time to be to have that measure. You would have to have a better response time, and that strain gauges give. In case of quartz pressure gauge also, you can have two kinds of uh, I mean strategies. Like you can run it little slower in the borehole where low liquid volume is coming out. So in that case, you will also get the good response with this. But yeah, that is a limitation, that this tool like response time is little bit on the upper side. So that's why you have to be careful to measure the pressure, and just slow down your running tool, and that will surface these kind of challenges. Gamma ray tool, it is very basic. It has a kind of scintillation detector. There is a generic gamma that every formation or every liquid, everything that emits. This gamma tool even records the gamma on the surface of the surroundings. That gamma radiation is not very much of use. So that's why we correct those environmental gamma, and we run this tool down to measure the gamma of the formation. This gamma is basically for the purpose to correlate the formation and tie up the depths, so that we know that we are going right in the direction. And that's why this tool is in the stack. Casing collar locator also, this tool gives the magnetic flux idea, and that's why where the metal thickness is high, it will give a larger magnetic flux, and that's how it gives idea of casing collars, and also it gives the idea whether somewhere perforation is done, and whether somewhere there is kind of leakage, casing or tubing leakage. So some fluctuation comes in this due to the magnetic flux difference, but again that has to be re-verified with other tools. Uh, this comes under the category of other tools that as I mentioned it in the second slide. Uh, these radiation tools are radial difference tools are basically consist of two caliper sort of thing, where these are 180-degree apart, and temperature sensor is mounted on these, and there is a kind of tool rotation that every tool has, and while running into the well, when this tool is being run into the well, the temperature calipers, they open up and they fix themselves to the casing boundary, and they measures the temperature variation. So as you can see that here the normal temperature tool is showing this kind of variation. Here some kind of cooling is being done in this particular part. So when this tool will be running, this will be showing the rotation is basically of the tool. As you see that here the tool is rotating. Once you have once you will be running tool with the Y line, there will be some torque on the tool, and it will try to twist and nullify that torque. So that's why it runs around the boundary, and it gives the idea. So here you can see that when the tool is running from 0 to 360 degree in this gap, it is showing the temperature variation, and that temperature variation is going on the lower side, and then I mean upper side, then lower side, then upper side. So uh, this shows that there is kind of 180-degree apart, there is a kind of perforation or something that has actually the cooling phenomena. And here there is a slight cooling phenomena, because here you see that slightly temperature is going down, but again it has recovered. Here it is very straight, so here there is not much of cooling phenomena is happening. This is more or less resembling the temperature profile that we run with the original temperature tool. So this kind of tool runs for confirmatory purpose. Yeah, there is no kind of any addition, but yeah, they give a much better idea that in which direction the cooling is being happening, even in the perforation. Advanced PL tool. These four PL tools are widely known in the industry. First is GHOST, that is gas hold up optical sensor tool, that is of Schlumberger, and they run it to know the gas holdup. This is based on optical sensor, uh, flow view. Time is actually little less, so I would switch on to the interpretation part, which is very necessary for you guys. I'm just briefing you guys on this. What you can do, I will share the presentation with you, and you can read it out, just for the sake of knowing the tool principle. That's it. So this is based on optical sensor technology. So what it does that the flow of liquid into the well bore, it has in the form of bubble formation mostly. So what it does that the when the tool is run, the light source is bombarded on the fluid, and these light source, when it comes out from this gas or water or oil, it gives a certain refractive index, and because of the reason that it reflects totally case of gas, and in case of oil and water, it is not very much identifiable. So in case of gas, the refractive index is very low. So this principle works in that case, and as you can see that in case of gas, it is near about air, and that's why what comes out as in the form that volume of gas, and that actually gives us the gas holdup. So in case of gas wells, this works wonder, and one if one has to run in the kind of solution to know the solution gas in the well, so this tool is ideal. Uh, in the digital entry profiling, there are micro resistivity tools that are, mounted on the caliper. And these tools basically measures the difference of resistivity between the water and hydrocarbon. Thus, it gives the hold up, uh, of water in this kind of multi-phase also, because resistivity of hydrocarbon, whether it is uh, water sorry oil or gas, it will show on the higher side than water. So in that case, if water is not fresh, in case of freshwater formation, if it is coming from freshwater, then you have to you would not get the water hold up. In that case, the situation will be dicey, because water and oil would read somewhere equal. So in that case, it cannot be giving the good result. So remember that in mind, that DEFT tool is for the formations where the fluid is water is saline, not for fresh water. And here its working principle is same like that. Only in the bubble flow, it will read the resistivity with the different caliper, micro calipers, probe tools, and those resistivities again converted to onto the surface into what kind of liquid is into the wellbore. Flow scan flow scan has multiple small spinners on the caliper only, like this, and these kind of arrangements give you the good results in any kind of flow, in deviated wells, or horizontal wells, or even in vertical wells. So these kind of tool where are being run in very crucial wells, where suddenly oil or water oil has stopped coming, and only water is coming. So what could be the possible reason? Or there is some other what kind of hold up, in case of what kind of hold up we are getting in the well. uh, it can be run with other tool like ghost and DFT to know that whether water or gas are there, and they are being miscalculated somewhere because of the horizontal or ultra deviated wells. So in such cases, this tool will give you the fair idea that this is not the case. Well is producing. We have to look for other remedies in to identify the problem. For the problem, we would have to look for other remedies. Ultrasonic flow meter and density tool are run in the well with uh, uh, together with, because density and this ultrasonic travel time, this gives the transit time in as a function of density. And this transit time gives you the this tool is basically been invented in Russia, and those there they have a kind of transmitter and receiver setup in which difference of travel time comes when it passes through the liquid, and that transit times gives the function of density. And thus this tool measures the density. And again, this in this there is no any kind of fluid flow volume related issue, because ultrasonic signals can range from everywhere in the casing area of any casing size. So range can be from as little as 10 cubic meter per day to as large as 10,000. So that is for that this tool is good. So coming to the interpretation part, this is basically what we have to think in mind when we are actually seeing this interpretation. Then, I mean, in this case, you have to have first thing in mind that read the log carefully, see the remarks as a reservoir engineer and production engineer, that what is being written by the interpretation team, what kind of queries that they have found in the well, those all those queries, that limitations that they will mention there, and with that those mentioned lines, they will have their interpretations. So read those remarks in the section of log, and see the tool stacks and well sketch, production data, etc. To actually know what is going on into the well. You know the problem. Suppose you have the problem in the body, and you want to first you want to know that how this problem is coming to my body before going to the doctor or some diagnostic pathology lab. You want to know yourself that what is actually going on, whether I have eaten something, whether I have worked out, I mean, very much, and something that has gone wrong with the body. You want to know first thing. So, as a reservoir engineer, you just think that you want to know the things in that manner. That what is the problem with the well in first hand. So, in that case, you would look for the workover and well-related workover plans. I mean, earlier past workover plans, what would have gone wrong with those workovers. So those kind of situations can give you a little bit of idea. Yeah, yes, in this workover, this particular thing was gone wrong. So this might have created some kind of problem. So if you give some kind of such kind of information with the production data and workover history, that will be very beneficial for the people who are going to run the production log. And these are some checklists. You can read it out. I am going right away with the interpretation. So this is the spinner response. Uh, Here you see that spinner is constant, and here it is increasing. Here it is increasing. Sorry. Here it is increasing. Here it is increasing, and again it is decreasing here, and then it is going constant. So revolution is increasing this side, and if you see it as up pass, like a tool is going upwards, and you are taking this, what would you infer with this? uh, See, if you are having this in the static fluid, certain RPS you are having revolution per minute, it is increasing, right? It is increasing. So you might know that, yeah, I mean, in production profile, what would happen that suppose here it is coming into the wellbore, and it is actually while taking the up pass, it is your tool spinner face is getting faced with this fluid. So it is actually increasing the RPS in that case. Here also it is increasing, but here suddenly it has decreased. It has got decreased. So what we can infer with this, that yeah, maybe there would be something with this spinner that might have got stuck. There might be some sludge or sanding with which this stuck up of a spinner would have happened. There might be reason change in diameter. Like here, you can say maybe say that this reversal might have gone because of the tool entering from the casing to the tubing. So here, as I told you, that in the inclined wells, convection happens, and other issues, due to other issues in and around the packer and the tubing mouth, you may see such kind of reversals. In this also, if you are going up, you are seeing that it is I mean, this is being lower. So in the past, if it is being RPS is being on the lower side, so you might infer that this is an injection profile. In this case also, injection is being done in the different at different intervals, like here, but here again it has suddenly increased. So you might think that yeah, here this zone may be giving the production, that's why it is suddenly increased here and again decreased. But the thing is that there is a kind of spinner reversal, and this is just that it has come to its original position here and again went away with the same profile. So here it has just sign has got changed, and there is nothing as such. There might be some local convection that is being happening, and due to that this may happen. And there might be some other problems also, like if you are like pulling up and in that case suddenly the winch operator has stopped the truck, and due to that there is kind of pulling sudden pulling of tool that may happen, and due to that also this kind of erroneous result can be given, we may get. Okay, so velocity, fluid velocity is what we actually calculate is with the spinner is with this formula. So RPS positive, as I told you, that it will be positive in case of if it is in first quadrant, and while your tool is going down and while your tool is coming up, it will be negative. So this formula will apply in that case. This is just because of convention and vector that we actually follow. Then with this velocity, we calculate the flow rate, that is Q, and in case of one phase flow rate, velocity is multiplied by the cross-sectional area, and D is the ID of the casing, and this correction factor comes from the Reynolds number that we had discussed earlier. So this we take 0.83 in case of western region of ONGC, and yeah, so this comes out as this. Yeah. Somebody has opened their mic. Anything?
No, sir. No.
Okay.
By mistake.
Okay. Yeah. So in case of, you can read it out here. I don't know. In case of a spinner log response, spinner readings generally decreases. I have already told you these things, but it is just to feel it out that spinner readings generally decreases with increasing depth. I mean, in down run in a producing well. So if you are going down, okay, and your spinner is generally decreases with increasing depth. Why it happens? Because that in producing well, when you are actually spinner readings actually generally decreases, it is not the correct thing. It is just that in that case you are actually facing that liquid coming out from the producing well, but once you pass that production zone, you will have a kind of scenario where I mean, what you are facing has suddenly got decreased. The fluid volume has suddenly got decreased. So in that case, you will not be having any kind of resistance or viscous drag. Not any kind, but minimum amount of viscous drag that will give you a kind of decreasing profile of this spinner. Spinner rate increases with increasing depth in the injector well. Okay, so in the injector well, it increases with increasing depth. So what it says that in case of spinner, when you will be coming up, it will be having kind of pressure and fluid volume maximum at the bottom, so it increases in that case. And a spinner may not indicate a stationary fluid in sump in gas producing wells. In gas producing wells, convection happens larger and more frequently than it happens in the oil and other cases, water production. So in that case, convection, due to convection, you will see that in sump, you are in sump also you are getting a spinner. I mean, some RPS is coming in that also. I mean, larger than the static ones. So, some, yeah, these are all like common things that from the density tool response you will be. I mean, in the sump, you will in front of perforation you will have to see the density response in case of hydrocarbons. In case of average of water plus hydrocarbons, uh, uh, this thing have to be looked in the interpretation that we'll see in the upcoming slides. Temperature log also in the sum temperature curve goes to geothermal. As I told you, that exception would be in case of gaseous production, where due to convection you will see the kind of lowering of the temperature below the production zone. In front of production zones, water, oil, gas, as it will be producing, it will take care of it. And channel behind casing we had discussed in with ideal cases. In the density tool, yeah, in the density tool, this kind of response you'll see, like water will be in the sum. Here it is perforated, and the gas and oil is coming out. So what will happen that in the sump it is showing 1 gram per cc, that is water, and here it is showing it is averaging actually with gas and oil. So it is averaging, and here you will see the mixture of both. So it is gradually decreasing, and it will again have a kind of average of gas and oil in this particular zone, as you can see in the wellbore. So temperature log also gives the rate of flow, how it can be measured. Like if production is happening from this particular depth, so in that case, if you are having a shut-in pass after 1 hour or 2 hour or 3 hour, so you will see that in that case you are actually getting your temperature decreased by a certain amount. So with that, an empirical formula is there that calculates. I mean, for particular decrease in temperature, this much of rate will be. I mean, this much of rate will be there for fluid that are coming out in the water. So there is kind of empirical equations. They have run several temperature logs in multiple wells, and they identified that, yeah, for 10 degree centigrade decrease in the temperature at surface in the profile, there is this much of flow volume is being decreased. So I will give you guys, if you want, that equation from some scientists. So I do not remember that. They actually give that equation, and with that you can measure the rate of flow even with temperature logs. With the capacitance, as I told you, that capacitance tool basically is important for water, and once it will identify water, it will give with the dielectric constant of water, higher dielectric constant of water, it will give the higher volume, and that can be calculated with that can be converted in the water holder. Yeah, so this is kind of log that we have. That's why I was actually hurrying, because time is passing by, and we have to look at this. See, how would you read this log? Every interpreter has their own way of looking at it, and as a reservoir and production engineer, you will also have your own way of looking at it. So these curves are mentioned here. This is gamma, black one is gamma, line speed is this green one, and pressure is this red one. This is casing collar located. This is our perforation zone. Here it is differential temperature. this is capacitance water holdup, and density is here, and temperature is this pink one, and full well bore, continuous full well bore is this green one. So there are so much of information coming from these logs. Gamma is basically for temperature tie, so sorry, depth tie. So this is not very much of contributing here. But just we would have to tie the depth with the open hole logs with this gamma, and that's it. And after that, what I do particularly, I first look at the density. Density gives us the fair idea that what kind of fluid into the well bowl. So when I have to make a story of in kind of inform and interpretation of this particular log, I will first go to the density log and see what kind of liquid is coming, whether it is justifying our production or not. As you guys have already given the production data, I mean, I am considering you guys as a reservoir and production engineer, so you guys have given me the production data. So I will see that, yeah, oil and gas is coming in this well, and density is fairly giving the gaseous response here. See, it is varying from 0.2 to 1.2. So it is somewhere here, it is reading 1. So it might be sump, and it is water here, and after that from June it is coming and decreasing suddenly to gas. See, this kind of fluctuation is happening in the density also here, just because here the due to the packer and this I mean tubing, this shows a kind of erroneous result. So you need not to think that this might be kind of due to some other reasons. uh, Gas actually convects here. So there is kind of gas packet uh, uh, that actually is uh, giving this decreased density value. So we need not to bother much about that. Second thing, what I would look at, that temperature, whether there is another zone that is contributing to it behind the casing. For that matter, we also look beforehand whether cement CBL VDL cement bond log is good or not. If it is good, well and good. In that case, we rule out one thing, that whether there will be any channeling or not. But if it is bad, then we'll have to look the possibility of channeling also. So in that case, if supposedly if there is channeling, so I would look for that. So second thing, I would look at temperature log. So if I am seeing temperature log here, it is showing the cooling anomaly. Here it is in the bottom part. It is mostly touching the geothermal gradient, and here it is showing the cooling anomaly, and it again goes along with this only. So I am confirmed that there is no any kind of channeling that is being happen, because here if some zone that is above this packer that might contribute as gas or something, that would have come into this temperature log with larger anomaly, but it has not come. So I ruled out all those things and come up with results, yeah, that this is only production is coming from only this perforation zone. And again, next on, I go to this flow meter. This is flow meter is the up pass and down pass are not shown here, because it is very clear in this case that if we'll go up pass, in case of production, it will increase. So it is the wellbore meter is increasing against the perforation, and in the sump it has some constant value near about 0, but after the production perforation zone, it is showing the fair value. So I'm convinced that this is actually production profile, and in this case d temp is showing fluctuation here, uh, to fairly show that this production, this is actually gas profile. This capacitance water hold up, this actually gives the idea that water water fraction is going down from this particular perforation, and here it has gone really down. So with this, this is qualitative interpretation, but with this we can also calculate the water holdup if water is water cut is less than 40%. This is another log. Here you can see the line speeds has been shown up and down in up and down passes. See, just this dn is for down pass, this up is for up pass. So these are line speeds, and this blue curve is gamma, and CCL is here. This is pressure log against this perforation zone. You can see there are several logs like full bore, well bore spinner down pass with 10 meter per second, 10 feet per minute logging speed, and then up pass with 10 per minute, 10 feet per minute logging speed. Then full well bore 15 feet per minute down pass, 15 feet per minute up pass, 20, 25, like this. Okay, so in this case, again, I would see first the density log. So I will search it out. Here it has been represented a little different from the earlier one. It is represented in the left side. So here it is in the sump. It is fairly showing, the blue one is fairly showing the water, and after that it has gone this to this like very low in around 0.225. So and this I'm convinced that this is producing gas. And let's come to the other one, that is temperature flow. Actually, this log is from of this one only, but it has been represented with the full well bore. That I wanted to show that you guys that how it is represented and how the temperature tool is sorry, tool stack is recorded. So this is recorded like this only. So this temperature would be recorded in first down pass only, no other down passes. This full well bore stack with 10 feet per minute down pass, this temperature would have been recorded, and other logs can be recorded, but there is no need. And we record in the full well bore 10 feet per minute up passes, density, and other log like capacitance, water hold up, etc. And after that, these all up and down passes are just for this full well bore. And to study its this and to calibrate it with its calibration that we have shown, whether it is production profile or not. So in this case, this is the zero line. Here you can see the negative side. So these are all will be kind of negative side, like when we are having the tool up. So these are will be all will be tool showing tool up, and these all will be showing tool down. You can see that with the color combination, you can see this after the presentation would be over. So this in this qualitative interpretation, I wanted to show you guys the casing leakage identification. So in this, see this log, this well was not actually active when this log was taken, and this in this well problem was that fluid was continuously coming, and that to water, and there was no idea how to control it. So we initially ran this temperature log to know whether from where it is coming. So the temperature log was run, and we got to know that there is some you can see temperature is actually increasing, because here it is 80, here it is 120. So it is actually increasing here, and goes on. So it is not gas. Just don't miss I mean, just don't confuse it with gas, because the temperature log is scale is read from this side. So in this case, fluid entry point is this, We were convinced with that, and now the problem was that that might have be casing leakage, because we would not have that. We did not have that perforation here. It was the first well in that particular region. So, say in that case, we ran another log that is called uh, multi-finger to caliper tool, that is MIT. So in that case, this multi-finger caliper has 36 caliper, small finger like calipers, that gives us the image of that particular casing. So in that case, we ran that after knowing this, and we got to know that, yeah, it is actually casing leakage. That also measure that multi-finger tool measures the flux of that material, and with that it gives the image of thickness of that particular zone. So we make image sort of thing, 3D image, and with that we come to the conclusion that it is casing leakage. So temperature tool had given us fair idea with casing leakage thing. Yeah, so this is another well in which we got to know that there is channel behind casing. So this is the temperature after 5 days, which is showing fair thermal gradient. Okay, this black one. And when it was run just after, I mean, in flowing condition in 1 hour, it was showing that something is coming here, and it actually gets the temperature gets increased and goes beyond this temperature gradient, and thermal gradient, geothermal gradient, and then again it increases here, and sudden decrease was shown after that. So what was inferred that something is actually coming into, because this was gas producing well, so something is coming into the well that is increasing, and we cannot see that adiabatic expansion here. The lowering of the log was not shown, so we were surprised what could be the reason. So this came to the rescue, that this gave us the answer that the some water source that is coming from this particular depth of 60, 60, 80 or something, and this is giving us this is contributing and coming to this zone behind the casing, beyond cementation, due to poor cementation, and it is increasing the temperature of liquid, and once gas is coming out, it is decreasing the temperature, but not as much as it would have been when without water channeling. So in that case, gas entry was shown, but the thing is that uh, not in a manner when what we see ideally, if gas would have come in only from the perforation zone. This is actually the profile of well, in which there are multiple perforations. So what could you infer from these two logs? This is actually full well bore represented here. I don't know if you guys can see it, because it is I wanted to show you guys whole log, so that's why I snipped it like this. You can magnify it after the presentation is over, and let me explain it here only. So I would go for the density log, as I do. I am seeing that this in the sum it is reading 1 point something, more than 1. So what I deduce from that there might be some slugs and some sanding that happens from these kind of perforations, that might have got deposited into the bottom part, and that's why it is giving a little bit higher density than what is of water, and it again decreased and have come to here to 1, and here to here it is only 1. So I thought that, yeah, it would be it might be that these two perforation zones would be contributing water. That's why it is showing the water density here. And after that, it has again got decreased to some point 0.8, yeah, 0.7 something. So then I came to the conclusion that this particular perforation here, it might be giving kind of light oil or something, which is showing 0.7 0.6 density, and that too, that might be with some solution gas. That's why it is in sorry, decreased. That's why it has decreased, and it is continuously came to here. Slight contribution is also from this zone also, because it is also showing decrease in the perforation here. Always you will see kind of due to convection. We have not represented cracker here, but due to convection, here you will see kind of anomaly, which actually is just to know that this kind of anomaly will be coming in and around tubing uh, head. So temperature had given me this idea. Now jump to this temperature. Temperature is showing the fair geothermal gradient here, and here also it has slightly giving us the idea that it has I mean, if you draw a straight line, it has gone upside. So these two this zone or these two zones might be contributing to the water only, but fluctuation is here only. So I am convinced that this zone might not be, this small perforation might not be giving this contribution. This bigger one would be giving. So this is the situation here, and after that, from this particular zone where I have seen in the density, the temperature also confirms that uh, this this zone is actually contributing solution gas and with oil, light oil. So that's why the temperature has little bit gone decreased. But again, if you draw a straight line, it has not gone beyond that geothermal gradient, below that geothermal gradient. So it is not totally gas, that is confirmed. And then again here you see that it has increased value of this this zone that is producing. So that's why the realistic picture of this temperature is coming here. So I came to conclusion that this zone and this zone are producing, and this zone is producing what oil, and this is producing water. So coming to the next hydro tool, that is capacitance tool. This is this is showing that actually the thing is that this is showing a little bit of lower side. That should not have happened, but the thing is that, as I told you, that if water will be coming and it is more than 40%, then it will not be giving the correct hold up, and that's why this is giving a little bit erroneous result. And jumping over to this full well bore thing, here you see that there are several passes up and down. Uh, in this case, you see, while in this pass, spinner flow meter is uh, going on decreasing side. So you might get confused that whether it is whether it is injection or production, but you have to confirm it whether it is up pass or down pass. And in this case, what have happened that we ran a tool in which uh, the pitch was on the negative side. So that's why the pitch was on the opposite side. So that's why this RPS is coming low, and uh, here it is again increasing because of the production. And here you cannot identify it much. Sorry, this zone is not producing. This zone is producing. So here you can see that this RPS is going on the higher side. Similar is the case with the downside tools, and you can see that this is going on in the same direction as this particular zone is giving that idea that this might be production, but sorry, injection, but it is production profile, and in the up passes, it is showing it has increased, because on the negative side it is increasing, but on the positive side it is decreasing. So this is not considered as correct one, because of again I told you that pitch was on the opposite side, so that's why it had given this of result. And in case of this production profile, production profile, it is increasing here and here. So again, I am convinced with this full well bore that this is very uh, giving us very fair idea that which zones are producing. In case of hydrofrac, you can run it in the pre-hydrofrac time, and in case of post-hydrofrac, pre-hydrofrac time, in the pre-hydrofrac time, this blue line represent the geothermal gradient, and in the post-hydrofrac time, this gives us the idea that fluid has gone into the wellbore quite good, and this vertical projection also shows that the vertical fractures have also developed, and this has gone up to this, and then again it is trying to come up to the this geothermal gradient. This is a gas injection well in which gas is being injected. So in this case, flowing passes are showing like a very little revolution, but this temperature you can see after shut in uh, 1 hour shut in, 2 hour shut in flowing 1 hour, 2 hour, 3 hour. It is showing that there is fair cooling anomaly that is coming into this particular well against this zone. So this is giving us fair idea that the injection is going well. Similar is the case with this also. Injection in this particular profile is going well, and in this particular zone is this injection is happening in this particular zone, and density is also showing that gas is being injected. After that, it is showing water or gas mixture. So that's why a little bit lesser than 1. Channeling behind the case, channeling to above. Okay, so in this case, channeling is being happening. So that's why see. This is temperature is of when the injection is being happen, and this is actually when in flowing condition, this will show us the true representation of what actually is the temperature of injection, and that will try to attain the geothermal equilibrium. So that's why it is slightly increasing. But after shut-in, 1 hour, 15 minutes, 1 hour, and 1.5 hours and 2.5 hours, you can see that kind of increase in this particular uh, part, and again it is decreasing here and going into this. So you can infer from this that if packer is okay, channeling above the injection well, this particular perforated part, the injection is being happening in this particular part, but this is behind the casing, this is going on to the top, and it is somewhere injection is being done in this part. So that's why the temperature of this part is replicating in this part, and that's why it is increasing. It is showing an increasing trend, and that's why it can be inferred as the channeling above the injection well. So that's it from my side. I guess I have taken a lot of time of you guys. You can throw upon questions and we'll try to resolve that. Okay. Hello.
Sir, can you listen?
Anyone who has any further queries can ask by unmuting themselves or could type in the chat box.
Can errors arising due to inclination be corrected later while logging, or other equipment should be used? Which method would be more efficient from industry point of view? Okay, so Bilal, from industry point of view, there are two things which we look into. If inclined wells are less than 45 degrees, we try to resolve it at our end with several corrections that logging that in-house softwares like Kappa and all provide. But beyond that, we prefer to give such kind of crucial wells to the Schlumberger or Halliburton sort of services team. So they have advanced well and they can run their Ghost and DFT tool to know whether in the inclined wells whether to actually know the larger picture of that well. So if the well is exploratory, so in that case we also give them to the third parties which have the better tools available with them, like FlowScan, Ghost, and DFT. So such tools gives us the better idea. So in that case, in this case, you see that operational cost is very important, and we discuss with the reservoir engineers and other authorities that we recommend them that in exploratory wells and other crucial wells which are parametric sort of where we want to monitor continuously the fluid dynamics of the well. In such cases, we do run the advanced log. Otherwise, we try to resolve it from the logging softwares only, like Kappa. I told you. Yeah. Can we measure the flow velocity of a particular phase in case of a multi-phase flow? Yes, Sandeep, we can measure. For that, I told you that we must know the hold up. Hold up will give us the fraction of that particular volume. And in that case, those fractions, with those fractions, the empirical equations are like that flow rate is multiplication of velocity of particular fluid like water and oil into the percent of hold up, fraction of that hold up plus 1 minus fraction of that hold up. Such kind of simple equations would surface in that case, and that's how we calculate the flow rate of individual phase. But the thing is that it is really from the industry point of view, it is very difficult to know that, because in the multi-phase it is like dynamics is like totally different to what we think that it would ideally have been. But yeah, so in such cases, if you see that suppose we will calculate that 50% water, 50% oil is there, we would definitely say fairly well that some fraction of fold up and density multiplied with the velocity of water, and 1 minus density of that would give us kind of value which will have which will give us the value of flow of oil. But our intention is not that. Our intention with the hold up is that from particular perforation, what kind of liquid in what proportion is coming, and flow rate is something which is I mean which is related with the fluid volume. Okay, what comes out at the surface, we do not see it as like only in the form of hydrocarbon or gas or oil or water. we see that we see it collectively. So our intention have not been our intention has never been like individually calculate each velocity, but it can be measured empirically. There are papers I will share with you where it has been measured. If there is a leakage, if there is leakage zone on one side of wellbore while the other side does not have a leak zone, how do we know where the exact leak is with reference to temperature log? Okay. If there is leakage zone on one side of the wellbore, please elaborate it what you want to say a little bit, because what I am understanding that leakage zone on the one side of wellbore is like somewhere casing leakage is just damaging one side and another side is not damaged. So
Yes,
how?
exactly, sir.
Okay, so in that case, that differential temperature tool that measures that particular direction in which, as I told you, that it rotates clockwise or anti-clockwise, and it gives us the idea that where in this 0 to 360-degree rotation, where it is going down or where it is increasing up. So where it is going down, in case of if gas is leaking, it will go down, and there will be having idea that from this particular in the wellbore zero. There is a directional tool also that is attached with this differential temperature tool. Like true north is given 0 degree, and in that case, if 0 to 360 degree, you are getting your temperature is increasing at 75 degrees, then you can guess that at 75 degree your leakage is coming in the wellbore. And for that we actually have a better tool to identify that. I told you that multi-finger tool that has 36 fingers, and that 36 fingers opens up like a caliper, and that is run in the wellbore, where temperature has given slight difference, and we make a kind of 3D model of that, and in particular direction, if some damage is there, it will give us the idea that leakage is coming from this particular direction. And anyway, if even if it has to be cured, it has to be cured with squeege and other remedial actions, which can be like after perforating, putting it, squeezing it with cement or other slugs. So in that case, it will be uh, it will be important to know that and perforation is like something that directional perforation we do if leakage or casing damage is quite large. If that is not large, we do regularly perforate it with regular charges that are surrounded, that are spirally put in the gun, and with that we squeeze whole zone, so that take cares of the directions. So in that case, we do not have to bother about direction. Yeah.
Okay, sir, got it.
Yeah.
Anyone who has any further queries can ask by unmuting themselves.
I think this is a quite large. The syllabus is quite large for production profile, and some slides I just skipped because I knew that engineers, you guys would not need it from the industry point of view. If somebody is asking tool principle, then you can go to through those slides. But I don't think in your interviews or somewhere in the industry from reservoir engineers, it would be asked. The interpretation is very important. If you guys do have any kind of doubt, I am sharing my email with you. I will be happy with resolving your doubt, and kindly mail me with your problems, and I will be reverting you once I will read your mails. Okay. Okay. So do share your problem related to production logging, and I will try to solve it out. And I will be happy because as an interpreter, there is always room for everybody, like you guys and us, to look at the picture in totally new manner. Okay, totally from the totally new glass. So in that way, you guys might come with some other interpretation pattern or some other interpretation story that can actually justify what we are getting in the form of logs. So in that manner, we and you are equal. Okay, and uh, just that these tools are run and we are getting experienced with these logs, that is only adding to our interpretation expertise. That's it. And otherwise, you would be thinking that how could it be, how could it be, and how could it not be. So just have to kind of queries resolved as as much as you will be having these kind of interpretations and interactions with petrophysicists. So you will be having resolved your queries. You need not to worry about that. Just that you have to be industry ready in a way that you are going to get interviewed, and you have to have proper answers for every kind of tools and every kind of production related problems, whether which tool will be run in that case. So I guess this presentation would suffice to those queries of industrial questions. So yeah, anything else?
So I think our session, and so it has been a very informative session for us. And we are all glad that we get to leave with more than what we came here with. We are grateful to you from the bottom of our heart that you took your time out from your busy schedule and made this evening insightful for us. Thank you very much, sir, for this.
Thank you, Umesh. Thank you, Anshu. Thank you, everyone. And we'll be looking forward to have sessions if you would want in future also. In coming to 1-2 months, I am a bit busy, but after that we'll be coming along. And if you want, just connect with me, and I'll be happy to help you guys. Okay.
Yes.
Thank you. All the best.
Thank you, sir.
Thank you so much, sir.
Okay.
Thank you.